The leaf, it turns out, is a remarkable piece of technology. Light lands on a leaf in quantum energy packets called photons. Every second it spends in bright sunlight brings a leaf thousands of trillions of photons. And almost every one of the red ones is captured and its energy processed. Let's trace the path of that energy through the plant. The first stop is the antenna, an assembly of hundreds of thousands of chlorophyll molecules. Hit by the photon, an electron within the chlorophyll will become excited and use the extra energy to bounce through the antenna to a bridging area. This is composed of a complicated arrangement of chlorophyll molecules. You can imagine it as an intertwined maze of roped bridges that, if you can find the path through, lead to the all-important reaction center. Once at the reaction center, the electron creates a permanently separated charge that is essentially energy that can be stored. It's the same thing that makes a fully charged battery such a useful source of power. At that point, the energy is safe and properly stored, ready for use by the plant. There's just one catch. The reaction center is a nearly impossible place to reach. Getting through the bridging area is a nightmare, and it has to be done quickly. The maze of wobbly rope bridges will absorb all the photon's energy if it takes too long to find the reaction center. A packet of energy has about 1 nanosecond to get across the bridge. Some might chance upon the right path and make it through in time. Most, though, won't. This is where the quantum tricks and Gregory Scholl's research team comes in. Their conclusion? Our results suggest that the energy of absorbed light resides in 2 places at once. This weird phenomenon is officially known as quantum superposition. It is written into the mathematics of quantum theory, which describes the position of a particle only in terms of probabilities of finding it in various different places. In certain circumstances, the particle can occupy multiple positions at once. And it turns out that to achieve the remarkable efficiency of photosynthesis, algae and their evolutionary descendants, plants, employ quantum superposition so that the energy can simultaneously travel along all possible paths to the reaction center. That way, it always gets there on time. As far as we understand it, when a photon of sunlight hits a leaf, its energy is passed to electrons within the leaf's chlorophyll molecules. Those excited electrons move to the reaction center not by random hops, as was thought, but by exploiting their quantum mechanical ability to take all available paths at the same time. It's such an exciting discovery because it raises the possibility that we could do the same. If the messy world of biology can exploit this quantum mechanical trick to the maximum by evolutionary trial and error, perhaps we can deliberately engineer the same feats to occur in our own solar panels.